Welcome everybody. I'll start the last and concluding lecture of this module on pointers and linked lists. I've gone through all the questions that you people have asked. So hopefully in the last hour when I'm supposed to do tutorials, I'll take up your questions and you can add more if you want to that list. Okay, so I have given you the material and my intent was that you would have gone through it. Okay, so that it will help me in discussing whatever I'm going to do now. So instead of going through the slides, I'll do a little bit of work on my paper and then I'll try and access the slide material which I've already passed through. So what we are trying to do, the motivation for now is to tell you how to design a linked list. Okay, what is a linked list will get clarified in the process. This is a single linked list. And as I said, is the core of creating many other data structures, which I discussed last time. So instead of discussing C directly, you rather look at the data structure and then try and see how you can write it in C. So I'm going to look at the linked list or a single linked list as a data structure. And why the name single? Because there will be only one link field for the moment. So I have given you some ideas about the layout of this linked list and I'm going to slowly build it up at the conceptual level. However, the implementation can be different than what I have said and we will look into that if you have other alternative suggestions from the participants. Typically, I have been drawing a linked list like this. Okay. Now we have to actually realize it through a program in a short while. Okay, so my representation has been a box, connected boxes, each box is connected and the last box has 0 or which is also known as a null pointer, which means 0 address. This is a null value. This pointer value is null. So firstly, as I go along, most basic clarification is that list will be built dynamically. The list is dynamic in nature. What do I mean by that? Is that the list can grow and shrink in size, and since dynamic data structures cannot be built anywhere, there is a very disciplined way in which such data structures are built. So I'll go back to two different areas which I hinted upon last time. One which is called the stack, this part of your implementation environment, and the other area which I'll call as a heap. If you don't use pointers and dynamic feature, then we use the stack only. This is the only thing which is used by our programs. Only feature required by our programs. Again, a single line explanation. A stack is used to hold values of functions at runtime. Okay, so what is in the stack? These are values of functions, data values, values of data, of functions, not other, no global out here. Okay, and what is in the heap? This is where the runtime entities are stored. Runtime data is stored. So recall. Now I'll be more structured manner. So stack will have some part of the data, heap will have some part of the data if it is dynamic, and together they will create the linked list. So the first clarification is this entity which I drew as list will be in the stack for the function who is trying to create it, and the entire box structure will be in the heap. This whole data, I'm going to show you slowly, is basically going to be in the heap. This is the only way you can create a dynamic data. So observe that the stack is static, which means that stack already knows how much data will be there, what is the type of each data and so on. So fixed data is allocated on the stack by the compiler, and the runtime data, the compiler doesn't care. The user builds, throws away, and all that is happening on the heap. So this is the conceptual view. Now let me draw only the part that I want and then see what do I need to build a linked list data structure. So now I'll draw the stack part only. For some function who is trying to work on a linked list, there will be, let's say, a place, I will name it as list for the moment. This is a place which is on the stack. And this is some function, don't worry which function, some function F. Some function F basically is trying to do all that. So this is a data area on the stack which will have a location for list, whatever list is. Don't worry about types because I'm not interested in C right now. Now this list basically must start where whatever data structures we use in programming languages, observe that if I use an integer variable, this is not a good declaration. A better declaration anytime is to initialize this value to something. So initialized data is always better than uninitialized data and causes less problems. So this is an initialized data. Is initialized with a value which is found relevant by the program. Similarly, if I want to create a linked list, which is a big data structure, we have to think of creating an initialized linked list. Every object that you create, whatever you create, a hash table, a sparse matrix, a cache buffer, a polynomial must have a nice, decent initialized data structure. It will vary from the data structure to data structure. So creating an initialized list is the first operation that I would like to do. How do I visualize it in my? So now observe that a linked list I've already said is essentially, so if this is my place for list, which is right now on the stack, I've drawn it here, eventually it will connect to something on the heap which will be like this. I hope you can see this. It will keep growing. This we said is on the heap. So now we are trying to say there is no list, there is no element in the list, or it's an empty list. How do I represent that? So an initialized list would typically correspond to what do I conceptualize as an empty list? A collection which has no elements, right? So this entire part on the heap is missing. That's how we start. Okay, so to create an empty list, basically it says that there are no elements on the list, in other words, and all languages which allow this basically will say that initialize a empty list corresponds to, you have to put an address here. The address is address on the heap. If you don't put anything, there is a data value. That data value will be interpreted as an address and something wrong will happen. So what we do is we use this special value treated as a pointer constant, which is called null or 0. 0 also compilers know stands for null. So you can use this special pointer value called null, which is a pointer constant. You can also get away with using the value 0 instead. Both go typically fine. And this can be used to initialize any address. So any address can be a 0 address, which means I've initialized with something which is not a real address, but I put some value over there. Okay. So this list, if you do that, the first caution is if you create an empty list, then one is not supposed to ask what is the first element. This is a wrong question because there is empty. And this is the only question you can ask. What is the first element to begin with? What is the second element? What is the third element? This is wrong. Okay, this is a wrong question because the list is empty. What does it mean otherwise? It means that a list which is empty should not be dereferenced. Okay. What does dereference mean? Okay. Which means that if you do list, so what I'm going to do something over here in a short while. Let me create it. This is not a linked list really, but it's just to explain pointers. So you know that I can use pointers by using a star. So I can say int star p. This is a valid pointer. I can say int I equals 20. Initialize integer variable. P is not initialized. And then I can say p equals address of I. This is all we have done in the past. Right? So this creates an proper initialized pointer. But before I have initialized, suppose at this point I ask system to say print. I'm writing in English, but you can say printf, give me the value of p. What is the value of p? He'll show you what is the value of p. I've told you. Every element has an L value. Value of p is what is stored in here, the R value. You can ask here what is the value of address of P. He'll also show you this address. If it is 2000, he'll show you 2000. If you have put 3000 here, he will show you 3000. This is okay. The dangerous thing to do is if you do printf star P. What does this mean? This says take the value what is over here and get me what is in 3000. So if I have done this, after this if I say star P, I will get the value 20. But if I do it here, then what has actually happened is ampersand P has a fixed value given by the compiler. We have not initialized P, therefore some junk is lying over here. And now we are saying go to this address, whatever this junk says, and try to see what is lying over here. If this address is outside the reference space, your address space, then there will be a segmentation fault. This we have shown. Now let me show with null pointers what I could have done. I could have done int star P equals null. So I've initialized. None of these I've done. I've just done this. After this, if I give printf of P, it will do something. If you say ampersand P, it will do something. If you say P, he'll show you 0 because this is null. Nothing is there in P. No address. If you say ampersand P, he'll show you the place where P is stored, the address of P. But if you do star P, even this will get to a segmentation point. Why? Because null is not a valid address. It is just an initialized thing to say, I will give you an address later. Currently there is no address. So the address 0 is not dereferenceable. Typically it is in the OSS area. Okay, so initializing a pointer to null is good. It only says I have created an empty list, and to this list I will never dereference. I will just use it for some other purpose. Okay, so coming back to where I started with, we want to create an empty list. Our intent is to do something like this, and I'm slowly building up stuff. I want to create this in a program, and we are seeing conceptually how to go about it. So what we said is, forgetting about the C structure, I will create an empty list to begin with. Okay, so this is the first thing I will do. We will have to see how to do that. Typically we will do list equals null, but this will have to be qualified. Like this it will not go through. What is list I have not described, but an empty list will be something like this. And then more important thing is I have to make the list grow. So I will assume like this. There are many ways you can grow a list, and I have given you in the notes 3 different operations. So let me show you the semantics here. One is put at the head of the list, which I have called push. I'm going to give more detailed semantics now. Another one I have called append, add to the end of the list. Another one I have said insert, which says insert by position. Okay. So let me now concentrate on these 3 only, and maybe I'll take one more operation in the same family, which I will call is maybe 2 more. One is called the length of a list, which says how many elements are there in the list, and I'll take one more, which is very important. I don't know what's happened inside the memory, so display a list. So don't think of C now. Think of these as operations to be done on a build list that is built. Operations in 2, build the list, make the list grow. I have nothing to shrink the list right now. Given a list, I want to find out how big it is, how many elements are there. And if I give you a list, you should be able to traverse the elements and show me the values from the first to the last. So empty list I have visualized in my box structure is, I will create a box called list, and I'll put the value null. I'm using the symbol 0, but null is okay. Forget about the type. When I want to create a single element list, it will look like this. This will be list all right. It will have an address. So let's say 1000. This 1000 will have an element of the list which looks like an element. Maybe I'm creating an integer list. So I've inserted, I want to add the value 25 to my empty list. This I have to grow piece by piece. So from this configuration, I have to go to this configuration. This is now recall is on the stack. This is always on the stack. And this whole thing is developing on the heap. So I need some machinery, I need some support. from the language, from the operating system in order to make this grow. This is the big jump from an empty list to a single element list. Okay. So in order to do this, I need to create these things on the heap. So the other operation which I need is, how do I bundle a data value or an element of a list into a packet like what I have drawn, a value which is an integer or whatever, into a box. This is what I'm doing. I'm putting in English only, because this box must come from the heap, right? So the system has to give us a feature. It gives us a very simple feature which is called memory alloc. I'll only use this. There are other versions also. So there is a built-in function provided by the C runtime system which is called malloc, which allocates some bytes of memory based on your demand, as many bytes as you want, if it has space. So we'll have to soon go through. When I go to the programming part, I'll have to show you how to use malloc if you do not know. Right now, just make sure that this is available, and all we need to know is how to use it judiciously, how to use it properly. So whenever I do a malloc, what will happen? What will happen is that I can get so I do malloc something. The result of a malloc is a chunk of memory. Effectively, you have to say malloc, let's say 10. I'll not do like this, but I'll show you how to do it. If you say 10, then 10 bytes of memory from somewhere in the heap, don't worry where, will be figured out, will be found for you, and the address of these 10 bytes will be returned. This is the return of malloc. Returns an address of, or the starting address of the allocated space on the heap. This will always be on the heap. Malloc will always give you space on the heap. So the first hurdle is crossed. Anything to do on the heap, all I have to do is a malloc, and I have to say how much space I want. System cannot, give you arbitrary space. You have to say how much space you want. So once I've got the space, then my first hurdle is, what I have done in the notes is, I've given you a function which I can look at it again when required. Function called make node, which does this. So whenever I want a box, I have a value, I want to package it into a box. So give me 25. This fellow will do this. Put 25 here, put this as 0, and return back to you. So my make node will do all of this and create a nice box for me, which is already initialized with the value that I want to be attached or detached. So now you observe, if I go back to 2, this is how it's going to happen. So I have the base case. To remember induction, you can see induction coming in a simple way here. Base case is an empty list. And that, without worrying about the details of C, I can just get this and get away. In my conceptual implementation, list equals null will create an empty list. Now what do I want to do? I want to do a push. So I want to do something like this. I will say push. So here is my list, and here is a value, okay, maybe 20. So if I do this is my expectation. My main program will do like this. The push is implemented as a linked list function. And what will happen if I do? I expect that this list now, instead of having null, will have a pointer to some location on the heap which will have this value 20 and null or 0. This is the picture I want. And this is a function that I'm going to define which does this properly. So I give it a list and it returns me 20. It returns me a box with 20 and this connection being made. This becomes a single element. So now see that the next small jump that I have to do, assume that I have a list now. This is my induction step which has n elements. This is my first element. Okay, I'm not writing the values, and it goes on, and there are n elements already in my list, and this is the end of the list. And we want to add the n plus 1th element, n elements on the list. Recall all the boxes are on the heap, whereas this is on the stack. If I want to add a new element, a new value, let's say the value is 100, what do I do? So I'll first say, please get me a box with 100. So for that, our details will be, I'll say make node, I'll give you a value 100. Please make something on the heap and return back to me. So what will make node do? On the heap, it will take a box, put 100 there, put 0 here, and give me this address. It returns this address. Let's call it P. So make node will do this. Put something on the heap which is not connected to the list. In some other area on the heap, he makes this packet and gives it back. So if I am doing push, what I want to do is, let's first write down the requirement and then see how it can be done. My intent will be to from here to go to this box which has 100, and this connects to the old list because I was connecting to the top of the list, and this is what I want the picture to be. This is my old list with n elements, and this is my new element added at the top. Okay, this is the intent, this is what I want to do in push. So observe, I want to get this, I have this and this, these two pieces. I already have one operation, I have done make node and I have created a box. So once you do this, then it's very sort of obvious that from going from n plus 1 to n plus 1 element list, there are some manipulations of the list which has to be done. Okay, this is already ready. So the first thing I have to do is, this is now connecting to this piece. So whatever the old list is pointing to becomes the successor of 100. So if say this is Q, let's say, then I want to put Q here and make this fellow point to this. So I've changed this address from here. I'm trying to make this picture. So the 100, 0 I have replaced by Q. So this is already connecting to this list. But this fellow list is still pointing to Q. So I now want to destroy this second operation and put P in here. Once I put P in here, this fellow now connects this automatically. This link is broken. Okay? Or in other words, if I don't draw the lower picture, I have drawn this. Now you can see, let me remove this, that this picture which I have done, I have actually what I have done, I have changed one operation here, which is change the next element of 100 to the start of the old list, and I've changed the value of the list itself from Q to P. If you take list, you will reach 100 as the first element, and then you will run down the entire list. So if we do it carefully, it looks like two address fields needs to be changed. Two addresses are to be changed and the job is done. So how we do it in C is a different matter. So I have to visualize this. I have to write a function which can take an empty list or a list with some number of elements, takes a new element and returns back a new list or returns the same list with one element added. So there is a lot of variations in implementation. Okay, I have chosen one style, so I should give you the style that I have chosen. Okay, but remember that you can do it differently also. So let me start writing now some semantics, some notation in which I'll explain my things. So first I'll start with create. It's very important. You may or may not agree with this, in which case the design will be different. So what does create do? So create to me is a function in the functional notation of set. So create, what does it do? It takes nothing basically, or actually it will take a list. So let's say it takes a list and creates an empty list. It makes it empty. So I'll show you how this can be done. The second one which I said is a make node. So I'm trying to give some specification. What does the make node do? Make node takes only an item or a value, whatever you call it. The list is compiled, we use the word item. So it takes an item and returns a pointer to a box which contains this item. These all I have to specify very quickly in C, which I'll show you in my code I have done. So make list takes one argument and returns a pointer. List creates an empty list, but basically it does not return anything. It makes the list empty. This is not really correct specification. I'll correctly write. The list returns nothing. Actually I call it a void. So it takes the list and makes it empty. So it returns nothing. There is no return value of the function. Make list returns a pointer. So this is correct. Okay, it just makes the list empty. And the third one, let me stop here and then do something important. So push, what does it take? Push takes a list. Cross in the notation means it needs this also, a second thing which is an item, and I will make it void. I could have made it a list also. This is my implementation, which means the push function will take an existing list, one item, and create a list which will be a a much larger list, but it actually returns nothing. So what does it tell you? It tells you if I do this implementation, there is a certain consequence of that. The consequence is this. So push will take a list. So here is a list, and this list points to somewhere. Let me assume it's a single element list. Does not matter. I give it an item also, 20. This is the input. What is supposed to do? Return nothing, but it should change something here, otherwise nothing will happen. So push will do this. It will take this list, change this whatever it was, say it was 5 value. It points now to 20, makes 20.25. This is a subtle observation, but makes it very clear, obviously. So suppose this was 1000 address. If this returns void, which means it doesn't, then it must change the internals of the list like this, which means it has to do somewhat like this. This is 2000. Here is 1000, which is the old address of 50. In other words, if I make the push function void, not return anything, then it must do this change destructively, it should change the list. In order to write something into a place, you must have the L value, which means unless I give the address of list to push, this fellow will not be able to work. So it has to change in list, so it must know where to write this word 2000. So I must know the address of list, which is this. So push, in order to work like this as a void function, void returning function, must be supplied with the address of the list because it wants to change the contents of list. So now all my functions as I go along, I'll categorize like this. Does the function need to change the given list, or does it not required to change the given list? Okay, so I will say, so is the write operation, so is the list read only, the input list that you want to work, or you need to write something? Depending on that, I will do different things. Or you actually are changing the content of the list. List is the header element, the start element. Do I need to change or not? These are the two things. Or you need to changing the value of list. Okay, lists. By list content, I don't mean a change internally. I mean right here on top element of the list. So just a small explanation, and then I want to go into code. So now I'm realizing, I'm trying to tell you that there are some operations which may require the argument list, the function that operates on it, to change the content of the list. Some of them require no change in the content of the list, and therefore I can take different stands while coding those functions. So what I'm going to do now is do this exercise mentally before I do C programming. If I have a list function, whatever be the function, and there are many functions that are given you. Some function, it let's say takes a list and takes something else, I don't know what, and it returns, let's say, void. Then I expect that if it's making a change, is this changing or not changing? Is it destroyed or not destroyed? Okay. This will decide what sort of decisions I take. There could be some other list functions also, which may take two lists. I've given a concatenation operation somewhere, and it returns a new list. This is different. It's not a void returning function. So when I do this, what I mean this list should not be changed, this list should not be changed, and I create a new list and give. So all the three lists should exist. But if I made it into a void, then probably I change one of the lists to code the result. It all depends on what you want. And depending on what you want, you have to code your C program. Okay, so before I get into the code, so what the design that I have given, make some assumptions, make sure you are comfortable with it. You can ask questions if you are not. So what I want to do is have a generic design, which means a design which is sort of extendable. So each box, each element of the linked list is important to me. A box is a single element. Single element of a list which is about to be built. We are trying to specify. Now depending on what you want to do, for example, I had given you in the programming exercises to write a program for polynomial as a linked list. Okay? And a polynomial has two data values, a degree and the coefficient, the degree of x and the coefficient. So it will require how many? It will require two boxes. The degree For the exponent value, let's call it exponent, that's probably more appropriate term, and a coefficient. So if I have 5x to the power 9, I want to put 9 in exponent and 5 in coefficient. So typically this is float, coefficients are usually floating point values, degrees are always integer, and you will have this. Box will be like this. So I'm trying to say, depending on the application, my box may have one or more values. The ones which I have done in the initial part of the code creates lists of single elements. So if you list of integer, then my list structure element will look like this. So my first generic idea is that if I want to create a linked list of values, I want to hide this detail of values. Is it a single value, single integer value, a single character value, a character array, a float value? I don't want to care. So this is the abstraction. I don't care how many data values you have. I want to create a linked list where this will be the basic idea. So there will be something called, I think I've called it info, and there will be a point. And this info I want to be 1, 2, 3, as many elements that you want. Okay, so you will see. Remember this, I'm going to show you what I have done to abstract out one or more values in the value part. This being a single linked list, this pointer will be to a box of the same kind. So this box also needs a name. So I need a name info to handle data. I need a type name to handle a box. Okay. And since my list which I have been drawing is basically a pointer to a box, so I also want a pointer to a box to be specified. These are my three elements in my type specification before I start the list. So remember, I have done three things. I want the data value abstracted out, I want the box structure abstracted out, and I want a pointer to a box abstracted out. And then I can develop linked list over many different applications. I'm going to skip some slide and let's concentrate on slide 46, okay, which is essentially an implementation of what I did on the paper so far. I assume you're familiar with type def. So the first type def says, for us, just a single integer will be treated as item type. Okay. So when I say item underscore type, it's in this implementation a single value. Now it should be clear to you, if I replace this type def int by a poly item and I put a float and an integer there, the item type could have been two values. So whatever comes after type def abstracts data. It can be a struct to have multiple values, or it can be a single data value, which is in this case an int. So that int can be comfortably replaced by a struct or anything that you want, and these are the data values inside it. So after having abstracted out the data value by a single integer for this implementation, we want to have a type name for a box. So the second type def that you see, which describes the type def name, is list underscore item. The rest is the structure. It has one value which is called item type, which is above, essentially an int whose name is info. See the box next to it. So info is item underscore type. Next is a pointer to the same structure, the box, and the box name is item underscore tag. And the second line therefore reads inside the struct. Next is a pointer to item tag. So next is a pointer to a box. Okay. Info is a one value or a collection of values. And this entire list item underscore, which means list type, when I say it is a pointer to list item. So now if you look at the picture, that should make it clear. When I say list type, it's a type. No space is created. List type is a pointer to list item, see on the right side. And list item is just a collection, which is a box, which has inside it another box, which is for data, and a pointer. Now if you change the definitions, a different program will come. It's perfectly alright to change this definition or change this specification. So now for a box, I'm going to use a list underscore item. Item underscore type to indicate a value in a linked list. And when I want a pointer to the box, I'll use list underscore type. These three names have been different. Okay, so let me move on. I'll only do two or three things in great detail. So now let's see, how do I create a list in my program? So what is my list? My list is something which will remain on the stack. So my list is basically the start address of a list. So it must be a pointer to a box. but pointer to a box has the name list underscore type. So I can shortcut, not write a long chain, but say my list is just list underscore type. It's basically a space for a pointer, and I've said 8 bytes for all pointer is my standard prescription, which is for my machine. So for my list on the stack, 8 and nothing else will happen when you do this. List underscore type is the name of a type, which is a pointer to a box. Box itself is another type which is described earlier. But my list basically has 8 bytes for a pointer, and it is uninitialized by virtue of what I have written on the first line. But we don't want to create uninitialized elements. So look at the next one now. I have a create function specification. My create returns void. It doesn't do anything. Doesn't return anything. It takes a list PTR, which is basically list underscore types pointer. The list underscore type itself is my list, right? If you take a pointer to that, you are basically saying the address of my list. That is list type pointer, address of list type. If you give address of my list to create as shown below, then this create function dereferences that pointer, which means takes my list's address, goes to the R value of my list, the box of my list, and puts null over there and creates the picture shown below. Okay? So this is my way of declaring types, which is I declared item type, list type, they were on the previous slide. Now I am building, I am creating objects, my list is created, and after creating my list is declared, and after that I call the create function to initialize. So in between the declaration and the creation or the initialization, if you dereference my list, you are 100% sure to get a segmentation. Okay, so this is how I have created my list. So I've shown you the specification, I've shown you a part of the main to which I will do. Now look at make node. This is trying to get you familiar with the syntax of malloc. Okay, it looks a long expression. If you have not done it before, I'll explain it in slow motion once, and hopefully it should be all right. If you go back to make node, what I said it will do, it will basically take a value, item type is int here, it will take one value or one or more values, and then build a box around it and return a pointer to the box. Item underscore type is to be packed into a box, and the pointer of the box is called list item, is returned. I could have also written it returns type. List type is list item star. The choice is yours. Now look at it. What the specification of the function does. The box, the picture I see below is what I want. I want this P back after the specification that I have given. So this long expression that you see, ignore everything and look at the malloc part of it first. It says malloc, and malloc says how many bytes do you want, right? So this fellow doesn't want to say, I don't want to say 4 bytes, 5 bytes. I say, I have given you a list item. List item is a box which has an item type, which is int and therefore 4 bytes, which has a pointer to a box and therefore 8 bytes. So size of list underscore item will be figured out by the compiler that a box of list item type, an int and a pointer, 8 plus 4, 12 bytes are required. So this call translates to give me 12 bytes. So this becomes a number by the compiler. The compiler figures out the size and puts it. So 12 bytes are being asked from the heap. This is what this malloc part means. Now look at something before that. So malloc is going to return you an address, like let's say 4500, and from there 12 bytes are reserved for you. But I want to treat it as a pointer of a box. So what you see on the left of it, in braces list item star, is basically called casting. So I've created a pointer, I got an address, but I want it to be an address of a box, and this is what I force by doing that casting. So we are saying if you give in 4500, please treat this 4500 as an address of a box of 12 bytes. This is what the writer is saying, otherwise you may get some errors. I can make a pointer to an integer, I can make a pointer to an array, I can make a pointer to a hash table. So malloc will return one address, the starting address. It's good to say what object is referred by this pointer, which I know, list item. So I make that explicit casting, and then in P I assign that. So the result of this execution, if 4500 address was found on the heap, then P becomes 4500. P equals 45. Now this value, the rest part of it, this whole thing is in brace, is compared with null. Is P null? Is 4500 null? The answer will be no in most cases. But there will be a time, there may be a time if you make consistent demand, the heap area will be exhausted. When there is no space on the heap, then the system will return 0. So for example, I can ask for 100,000 bytes by making my list item very big, and the heap has only 400 bytes. It will say 0. Sorry, I can't serve your request. I return you 0 address, or by saying that there is no space on the heap. So if you ever get P as 0 after the heap has been consulted with a malloc, then I give myself an error by saying run out of memory. I know there is something wrong. The heap is not able to address it instead of me being thrown out. If that happens to be null, I don't dereference that pointer and create a segmentation fault, but I'll do run out of memory, and probably I'll quit the program and come back and see why things went wrong. So the error is an indication to the user, to the writer of the program, making him or her remember that this is not the correct path to be taken because the heap is exhausted. If this is a valid address and it is not null, then see what I am doing. Now I've got a pointer P which is uninitialized. So now I say P arrow info. Info part of the box will get an integer. Item is an integer. So in P arrow info part I put the value. P arrow next, the address part I put null, and then I return this P back to the user. So all this hard work of taking a value, packaging it into a box and returning the address of the first element, also making the next element 0, has been very decently done by me. It is not necessary to write this here. You can actually inline it in every code that you are writing, but I find this useful. There is a designated function whose job is to create a box and return the address for other functions to be made. So what is important here? The proper use of malloc and testing the result of malloc immediately before trying to dereference P. So look at the else part. The else part I am dereferencing. If you have given me 4500, then I am saying in 4500 to 4503, the first 4 bytes, I am going to put the integer value you have given. And from 4504, for the next 8 bytes, I am going to put 0. Okay, so this dereferencing of 4500 is legal because 4500 is a genuine address. If it is 0, you cannot do it. So the dereferencing is done only for a genuine address, and make node should work properly for any number of times that you run it, including when P is exhausted. Okay, so this I have discussed. So this is push. I've told you already there. So now let's look at the semantics of push. So look at push. Push says you have to give me a list, and list means I must have an address of a header of the list. Okay, so I must have a pointer which has the header of a list. So what is list type? List type is already, so observe here. Let's see if I can go back and show it to you. So what I said is my list takes a list, takes an item and returns nothing, but does the change as a change to the list, addition to the list as a side effect internally. In order to change this value of 100 to 2000 or 1000 to 2000, I need the L value of list. This is what I said. Unless you do this, I cannot change the content of list. Only through L value I can change. So what is list, and therefore what is address of list? So observe that list contains, so now let me go back to my names. I have something called list item. Remember that list item is the box. This contains item type, I am ignoring. My list type, when I say the list type box basically has a pointer to this, which is basically what my list is. And in order to change the content here, I need the address of this. So I need the address of list type, which means I need an entity to create which is list type star. So no wonder therefore the first argument of push in my implementation is not the only way it can be done. It can be done in many different ways. My first argument is list PTR. This is basically an address of a list type or pointer to list type. Second one is a number, okay? An item to be inserted. So what do? I do list item star P. So I create a pointer of the right kind. I could have combined the first two statements also. And in this P, I call make node and get a boxes address here. This is not the list address, this is the boxes address. List item is a box and P is a pointer to list item. So I get the address of a box from the heap in P. Again I check. If P is null, error, no space in heap, I return from here directly. I don't do any push because I can't do it. Else, if I find that no, I have got a genuine box returned back with a value bundled inside, then all I have to do, as I showed you in one of those earlier slides, 2 pointer manipulations, if you recall. Okay, that's what I'm going to do now. I already have a list with n elements, which is at the top. I want to make it n plus 1. So I did it in this order. I did this first, okay, and then I did this. These are the 2 operations that I want to do. The first operation takes the current value of P, which is returned from the heap, connect it to the old list, and then I change the list. Okay, so if you look at this, you will find I have exactly done that only. So P arrow list, the new node on the heap is connected to the old list, and then the old list pointer has changed to P. And doing this star list PTR equals P is basically that makes me require the address. So now it should be clear that if you want to do a push, then you don't have to give me a list, you have to give me the address of the list. So the use of this push will be create a list. So let me show you a list. So if I have created it like this, then my main program, if these 3 functions I want to use, then I'm bound to do like this. Suppose I write a main with these 3 simple designs done. Okay, so I can give something on item type. Maybe I can call it a value and give any names to it. Okay, I want to create a list. So for list I need a list type, and this can be my list. I can do this. I'll show you what I'm trying to do. The underscore type, these I've defined already. So type definition. Then I do create, and I'll do address of my list, and I'll see what happens. Why I'm doing this? It has to be consistent with my function definitions. Okay. And then if you want to do a series of pushes, I can do this for I equals 0, maybe I less than 10, I plus plus. I'll do push to my list. Maybe I should read the value here, so maybe I'll put a val. So let me insert, I forgot. So I'll do scan f of address of val, put the format accordingly, d or whatever. Okay. So I read a value and I push list val over here, and my list will keep building up. Let's see why. So let me go to my type specification. So remember, item type val means it is an int. It's essentially same as saying int val. So I've created an integer space for val. List type my list. What is my list basically? These are all on the stack. So my list basically is a pointer to list item, which I have not defined. Here, it is already defined there. It can point to list item. This is supposed to be point to list item, but I have not put anything over there. It's supposed to be a pointer to list item. Create and my list, if you go back, the create will take this address of my list and it will put a null over here because it can destructively put a value. This becomes my empty list. Now let's look at push. What does it do? Suppose this address is 1000 of my list. So this says, please give me 1000 and give me a value. Suppose I give him my list and say the value 25. Then what does this fellow do? It goes to the heap, puts the value 25, puts 0, and maybe gets the address as 500, which is returned back. And what does push do? Push says, I want to change this null now. Here's the dangerous part. And make it with 500. So you can change this content of 1000 if you know what is 1000. So I have to give him address of my list. And therefore I'll define push also, as you have seen on the screen, so that I can pass him addresses of these entities. So push is list type underscore list PTR. So I give him an address of a list, okay, and then it can change it and return back, and therefore I can get away with void. So if you have gone through this, I'll assume I'll not do the rest. If you have doubts, you can ask me and then I'll discuss. Observe that in length, the length which I have given list underscore type star list PTR. Now I'll ask you a question on this so that I understand whether you are understood it or not. Suppose I don't want to give list underscore type, but I want you to rewrite this function with list underscore type only. Remove the star. Okay? So I'll not give you the address of my list, I'll give you my list itself. Will this function run and what changes will be required? Why am I saying this? The rationale is that list, when you want the length of a list, I'm not going to change the list. I'll just run down the list, taking the first address, the first element, then the next address, the next element. I'm not changing the list. So why should I give you the address where my list is? Okay? And that is a dangerous thing to do. So this is my observation. So I've written it deliberately so that you improve it quickly. So here is my length function. As given, it takes a list underscore type star, okay, and what does it return? It returns an integer. This is what it does. What am I giving it? If I want to call it, therefore what should I call? If I want to call, I have to call length and my list in the current specification. Why? Because suppose this is my list. Suppose it has some 2000 and it goes on to the heap and has built up a list. Suppose these are my 3 element list out there. What my current thing says is you have to give me list underscore type star. What is list underscore type? List underscore type is defined type def as it is list underscore item star, and list underscore item is a box. So this is list type. This is what is list type. If you want list type star, which means this is my list type, what I am storing here is list type. It is an address of this, and you want the star of this, which means I want this. So if I give to length this 2000 and my length function has been wrongly written, by mistake he changes this 2000, I cannot do anything. He will change my whole list. Finding the list, finding the length of the list, he may destroy my list. So I don't want to give you the address, I want to give you only this. So I want to give you only 2000. I don't want to tell you that my list address is 1000, which is what I am doing over here. So I want to rewrite this so that I don't want to do this. It's an unsafe operation. List does not require it. I want length to be called with my list only and not its address. So it can never change the value of 2000. It can run down and say there are 3 elements and that's what it should return. Okay, so I have many of my operations that I have done. I have given it everywhere the list address, which means you can go ahead and dangerously change the content which may not be required for this. So length is a read-only function, and why have I given it? More to make you point out this mistake. Okay. The first one I pointed out to you. So if I now change list type underscore star list ptr and remove the star, I can give any name to it. So list type is list ptr. Then what change do you think will happen in the rest of the code? Because instead of a pointer, I have given you the object. You should be able to figure that out. When I take up the question answer session, I look at that. If you can do this one correctly, it should give you, I'll get a feel that you have understood what's going on. So again, I'll repeat here. You think, if you get the answer, you don't have to tell me. If you don't get, tell me. So what my question is this. I'm asking you to change my specification. So I want to delete that star. Then any name is fine here. I'll continue with the old name. List ptr is just the name of a variable. I want to know what change will happen inside this code since I have removed this. What changes are required? And let me tell you, very few changes are required to make it gear up to a safer version where I don't give you the address of my list and therefore you can change the contents. I only give the address of header of the list. You can only go to the header and do whatever you want. Any change that you make will not be visible outside the list. Okay, so just to run down the remaining slides. The remaining slides are similar. I have not explained them. So there is a display function. I'll just keep commenting. The display function, again, what it's supposed to do? It's supposed to take a list and show you the elements. First element 3, second element 20, third element 45, fourth element 56, whatever. It just traverses the list, walks down the list from the first to the last element and displays it. Otherwise, you won't know what is there in that. So again, you have to tell me whether list should be a read-only function, which means it just takes the list, doesn't change it, but just displays it. Or should display be a destructive function where it may change some content of a list, and the current implementation, is it viewing as a read-only or is it viewing as something which can be changed within the code? Now, depending on your comment, you have to rewrite it or you can accept it as such. Once you accept a certain way of doing things, then it will also impact the way you call display. For example, given this display, what I have given, I can ask this question. The quiz does ask some simpler questions of this kind, so you should do it without running the program. Running the program will give you the answer. So I had given my specification, and this is my question now. Void display. You must have had enough time to look at this. List underscore type star some list ptr. This of course is a chosen name, okay, and there is a specification. I want to use this in my code, use this function. So I'll assume that I have created a list. So how do I create list? So I will have list underscore, what is the type I have said? List underscore type my list. Okay, then I will create, which means I'll create an empty list. So I'll pass the address. This is because create wants this. Now assume that I have populated with push or whatever. I am not going to write this. So I populated my list with some number of elements using push. So I have written that for loop or whatever. I have pushed elements. Now I want to display my list. So should I use display my list? Okay. Should I use one or this, or display address of my list, or should I display star of my list? All of these three are feasible, and why? Only one is correct, the rest two are wrong. They are compile time errors, and they will also not do the correct job if you do. Only one is correct, and you can ask why. This is what I am asking. So because I have displayed in a certain way, I have created the function with a certain signature, with a certain specification, I am forced to use one of these. So my question always is, if I change the signature or the argument type to only list underscore type and drop the star, what change will be inside the function and what change will be in the call? Both will change. Once you become comfortable with these changes, changing the specification of your program from one to the other, then you would have understood how to deal with pointers smooth. You will have to make mistakes, correct, okay, figure out why the compiler has given error, analyze it, and then you would know that there was a major reason why. Okay, so there is a linked list design, there is a main program which I have given you. I have also given you many linked list operations. If you want any of these discussed, you will have to ask me. Yeah, I'll move over to the question answer session or the tutorial. But I have given you a find which is useful. You want to find if an element is there in the list. You have no direct access like an array. You have to take an element, run down the whole list. I have given you some different options for find. Is it present, absent? Is it present how many times? And in which positions is it present will give you different variations of this list function. I have given you a specification of append, where you want to add an element at the back of a list. Okay, I've given you the implementation of find. Okay, so that's fine. I've also given you insert and delete, two different operations. Okay, insert will allow you to create a sorted list as you go along and build a list for whatever reason. Delete will allow you to remove elements from a list. Now, depending on which version you want, there are many options out there. I've given you some reasons and the code for insert, which I don't want to discuss unless you have a problem. I've given you a code for delete also. I've given you a way to create a linked list, which is the reverse of a given linked list. Sometimes it is useful if you want. I've given you a concatenation of two linked lists, join two lists and create the new list at the end. I've given you reverse of a linked list, code out here, check if there are errors in each case. I've given you concat, and then I've given you a main program which uses all of this. Okay, so this is what is there in my slide, which is by no means complete. You can add lot more functionalities and you can build up other linked list design. So I'd like to conclude the lecture part only by saying that once you have understood what is a linked list, you have understood what part is in stack, what part is on the heap, how you can make it grow or shrink, how to write a new operation which is not there, okay, and so on, and then you sort of you can then try and solve. For example, since I've put in the assignment, so I'll just give a little hint about, many of you have asked what is the use of a linked list. So this is an assignment problem, but just to give you a conceptual issue, In the maths world, you have polynomials, okay, which is something like summation aix to the power I, where I goes from 0 to whatever, some n, and qx could be another polynomial, I equals 0 to m, and maybe not a, but maybe some b, bi and x to the power I, and so on. You have many polynomials, okay, and you want to do polynomial arithmetic, you want to do px plus qx, you want to do px minus qx, you can do also modulo, you can divide a polynomial by a polynomial. So a lot of operations are done. Polynomials are very important in many fields of computer science and electrical engineering. The point is that the polynomials are sparse. If I have a polynomial like this, x to the power 200 minus 2x to the power 90 plus 5. There are only 3 terms. I don't want to use an array where there will be lot 0 coefficients. So people represent such polynomials in this manner. 200 is the highest power, coefficient is 1.0, the next element is minus 90 is the exponent, minus 2.0, this points to coefficient, exponent is 0, the constant value is 5, and this is the end of the. So I can do with a much shorter representation, only non-zero terms are kept. Similarly, I can represent qx. So now I need a new, this is a linked list. I need a new operation on a linked list where I want to add two linked lists. It is normally not done. Linked list we don't add. But this linked list represent polynomials which are mathematical entities which can be added, subtracted, multiplied and so on. And therefore I want to support a function which is add, let's say a poly with a poly. Appropriate types can be defined and that returns a polynomial. So all these I can do. So depending on what application you are using a linked list, it can give you new operations to be supported to solve that application domain. But it's not difficult because you already know how to create a linked list, you know how to traverse a linked list, you know how to manipulate linked lists which are one or more in number. So solving an application requires that you have understood linked lists properly. You can code any function that you find useful and then you transfer over to your domain and solve a problem in that way. Okay, so with this I want to take up the question answer session or whatever else that you have. I'll look at the old question that you are given. You are of course welcome to give me more. So I'll take a short time to see your earlier questions. I have some of them. Now I am at a loss sometimes to figure out which answer should I give because I am not too sure what is your background. If all of you are first year students, then I can answer in a certain way. But if there are first year, second year, third year sitting together, then the answer will be very different. Okay? Even for the questions that you have asked. Okay, so first I'll look at the questions for today and then I'll see. So there is one question I can see which says what is rehashing. So though I've not covered hashing, I'll probably tell you what is rehashing and so on. So I'll take that as the last question, I should not forget. So I'll just run down all the questions quickly. If I've answered, I'll say I've already answered. If I have not, then I will answer it. Fortunately, Nisha, who is my TA, has given me a printout so I can see all of the questions here. First question, what is the size of a pointer variable? So I can give you the philosophy. Typically earlier it was 4 bytes and you can see why. For a long time initially, 4 GB of RAM, okay, this was considered to be very high. People used to work in kilobytes and megabytes and so on. So it so happens that 4 bytes, in 4 bytes you can store an integer number which can go up to 4 gigabytes, which is 2 into 10 to the power, whatever, 4 into 10 to the power, 2 to the power 30, 2 to the power 32 basically. So when your RAM exceeded 4 gigabytes, then there are more memory which can be addressed beyond 4 gigabytes, and then all the implementers changed over to 8 byte pointer. To 8 bytes you can handle much more memory than it is. If you have 8 bytes, you can store a number as large as 2 to the power 64, okay, and there are no memory anywhere close to it. So that helps us. So the size of a pointer variable today in most architectures is 8 bytes because the memory has become big. Second question is what is a wild pointer? So there are many such terms people have used, wild pointer, dangling pointer and so on. So the point that you should note down is that when you introduce a pointer, which you do by saying T star P. T is the type that you want, which could be your type or the built-in type. So T star P creates a pointer of type T, which I have not specified. And then if you don't initialize it equal to nothing, then this is a void pointer. So I have a location and no location is free. It has some value. Every value can be interpreted as an address, right? Because 32 bits also will give you an address if it's an integer, whatever you have. And you can go and access that address and you will get wrong results. So a void pointer typically, if I'm not wrong, is used to indicate a pointer that has not been initialized and therefore is a potential error or a bug in your program. Our sir has told that int has 2 bytes, but you are saying 4 bytes. This I've already answered. Don't trust anybody. Just write a single line program, printf size of int, and you will know what is there on your machine. How and where to use void pointer? Okay, there are a lot of void pointer questions. Let me take them all in one. Fourth question is how and where to use void pointer. Next one says, what is a void pointer? Somebody has said what is the concept of a generic difference between null pointer and void pointer. All of these are around the same topic. So let me for once clarify the difference between all these terms. So I'll use my paper. So the things we are looking at is, I'm going to put all of them together. Void pointer, generic pointer, and I've shortly explained what was that. Wild pointer, some people have also used, I refused to answer last time, huge and far pointer. These are all relevant depending on which year you are in. If you are in first year, I would not like to confuse you. These are all pointers, adjectives, dangling pointer and so on. Okay, so null pointer, as you saw, I was trying to initialize something to equal to null. So this is the null pointer. In some sense, it's a value, it's a pointer value. Okay, and it can be a cause of confusion, but in some sense it is overloaded, right? For example, I can write, so null pointer is basically a pointer value, like 0 is an integer constant, quote A, quote is a string constant, is a character constant and so on. Null is a pointer constant, and you can initialize any pointer to null. Okay, you can say float star x, xp or whatever equal to null. Okay, I was also taking a pointer to item, let's say a list item, which I had done there. I can create a pointer to it and assign it to null. So null pointer, you should treat it like this. It's a value which you can assign in any box. Okay. But you only assign it to a box which you already have decided what it should point to. You have specified what is p int star. It should point to an integer. You are supposed to put an integer value here. But eventually I will put that. Currently I want to put it null by saying I don't have a value. Okay. So null is in some sense a generic constant which you can put in any pointer or a pointer to anything. So xp is a pointer to float, but I initialize to null. It is not pointing to anything. So null and 0 in some sense you can treat as synonymously. They are address constants which don't mean anything. They are initialized, but they are not dereferenceable. If you dereference a pointer initialized to null, you will get a segmentation. So a null pointer is somewhat like a pointer constant. What is a void pointer? Somebody asked, where is it used? I would generally say don't use a void pointer. It's a dangerous thing to do. Unless you have requirement like this. You are short of space, and let's say you have different objects. So here is an object of some type. I'm putting different shapes. Okay. So these are different objects. And I want to have a pointer P which can one point in time point to this. Later on I want to change this and make it point to this. Later on I want to change it and I want to point to this. Typically somebody will say, why don't you introduce P1, P2, P3 and let them point to their respective objects, right? But the point is no, I don't want to do that. Okay, so instead of having 3 different pointers and let them point to the respective object, these are different objects. Let's say this object 1, this object 2, this object 3, totally different. The pointer is an address, so it only is an 8-byte entity, just will put some value. So if you want to, in a scenario where the same location has to point to different objects, then how do I do that? So then we do something like, I create a void star P. I can even assign it to null. So this says, what does P point to? I don't know. I don't know the object that P will point to. So it's a type. So the type is not given. And later on, I can put P to whatever type I want. Okay? So T star whatever. And then I make this pointer to be forced to this. So I can force it and assign it to something. So void pointer is used where I know that I have a pointer, but I don't know which object it will point to. I don't know the type of the object. So I define, this is also generic pointer. If I say void star P, essentially I am saying I don't know where P will point to, but it is a pointer which can be attached to any object as and when I want. So generic pointer has the same meaning, that I want the pointer to go to any object. Void pointer is also having essentially the same meaning. While pointer is uninitialized, so it is not initialized, there is some problem. Okay. Dangling pointer is a pointer which is pointing to nowhere. How it can happen? It typically happens when you allocate a memory from the heap. So suppose this is P. Okay. This P I have stored some address which is actually on the heap. There is an address over here. This P I have stored. And most programs, decent programs will use like malloc something called free. When I say free, then this pointer is restored back to the heap. This becomes free on the heap and can be reallocated. This link is broken. However, the address of P continues to be here. If it was 1000, this continues to be 1000. P is not destroyed because P is on the stack. It cannot be destroyed. So after I have done free P, I have this address 1000, but 1000 is not linked to it because I have surrendered it back. Now if I reference P, this P becomes a dangling pointer. With the pointer to nowhere and dereferencing it can actually give you segmentation fault. Another related question I found somewhere, people have said, what is double free? I was first not clear, and then somebody made it very clear by saying, what if I do this? So I have P equal to something. With a lot of effort, I've done some malloc and I've got a P. Yeah, I don't know what you have done. I don't care. There is some type over here. And then I do free of P once. And then I do free of P again. I can do it any number of times. So the question somebody asked very explicitly, what happens if I free the same pointer twice? Okay. So one answer to such things will be write a small program and see what it does. The more interesting part is, can we explain what it does? Okay, so let me try and explain again in my short thing. So you have done this. What you do when malloc has been done, here is your stack, and on the stack there is a place for P. And P has an address which is there on the heap. This is what has happened. This space has been returned back to the heap. What does it mean? If you want to look, you should have a little bit idea about the heap. So the heap is a big structure, and the manager of the heap basically has a clear idea about what are the free memory and what are the occupied memory. So he is dealing with it. Okay. So if the heap has 1 megabyte of memory and half is full and half is empty, he knows which bytes belong to the free memory and which bytes belong to the occupied memory. So once you do a free, his free memory collection increases. He gets more in the free memory. Okay. And from this free memory, he allocates memory when we ask for do malloc. So for malloc, he will give out from the free memory and it will become occupied as a result of malloc. And when you free something, then it goes to the free memory. So when you do a first free, whatever you have done, this was the picture. When you do a first free, this has gone to the free pool and it is available for reallocation. However, as I said, this address which you have already stored here cannot be destroyed. Okay, either you put some value in P over here, null or something, and make sure that you don't rereference it, But if you go and dereference it again or do any operation, now you are saying again free P. If you want to do a free P, now this fellow will say what is 1000? 1000 does not belong to you. 1000 should be in the occupied memory if you want to do anything. It should be in the occupied part of the heap. But 1000 is not on the occupied heap because you have freed it. So what will happen? Uncertain things may happen. Most likely it will give you a segmentation fault again, because you are trying to dereference a memory which does not belong to you, strictly speaking. It is not part of your occupied memory, it is part of your free heap memory. Okay? So double, triple, free, second doesn't give you trouble, probably the third one will, and so on. So if you do something, if you try to free the same memory twice, there is a semantic error, because the first free has already surrendered the memory and that memory does not belong to you. Access it again is an error. Dereferencing it is also is an error. Let me see if I have left anything. Huge and far pointer. Typically these are not relevant today unless you are reading some old textbooks. Now this answer should be only consumed by senior students, first year writes ignore. Because if you have done an operating system course or if you have seen how code is generated by a compiler, then this will make sense. So those were the days 20-25 years back. Because remember, you write source code and the source code does have loops, for example, for loops, if then else's, repeat loops, while loops, and so on. What does it mean? It typically means, if you look at the compiled code, again, those who have done compilers OS courses can appreciate, these are low level code, and a for loop will have somewhere a jump statement, go to. Go to where? To the first statement. So maybe go to 100, and 100 could be this instruction. These are all instructions or labels. So now when you translate and address an assembly code for it, there are different varieties. The assembly code typically in most assembler will have a jump or JMP or some such mnemonic instruction. And after this, it will tell you about a label. So this far and wide near jump basically say, if you want to jump in the code, is this a near jump? Is it in the vicinity of the code or is it far away? Why was this important? Because memory was less. It was fragmented in small parts. So a far away jump meant you had to do a long translation instead of a simple one. Today all those issues have gone. Whether you have a near or far jump, the system knows which jump instruction to use, and it can handle all these short and long jumps almost in a same or similar fashion. So today's systems, these are not important. There is a similar thing in OS which I don't want to get into. So for you it does not matter whether you are writing a million-line program and you are jumping from the millionth statement to the first statement. It does not really matter, the system will take care of it. So don't worry about this. These are not really concerning us. This is more concerning the implementation part. Because if the jump was short, then this could be done, for example, by a 2-byte memory. It's only 128 bytes away or something. If it is a big one, then I need a long jump instruction which takes more memory cycles. I hope this satisfies you. But it's not really directly concerned with C and programming. It is more concerned with the implementation of the environment. What is the, how many types of structures are available in pointers? So this question was not clear to me. So I think I answered that there's no limit on the kind of structures you can use using pointers. Pointers are used, it's just an address field, and you can put address field and package it to create whatever data structures you want. In my slides I've given you some, and you can create any more than that. So there is no limit. Any complex structure you can create using pointers. You can have as many pointers in your data structures as you wish, but they have to be finite. Size of pointer variable be modified, I don't know. Address of main function, I told you right in the beginning, write ampersand any function name, that will do. There's a question said, what is the meaning of %p? %p typically is used to print out a pointer value. Like %d is for integer, %f for float in C, %p is for pointer. So if you have an address, use %p specification to print. How pointers can be used to write efficient program in a sense of execution time and memory uses. Okay, these are very tricky questions. Typically you should not use it unless it's really required. But most people use pointers in place of arrays for efficiency. So it turns out that arrays are indexed through pointers. Instead of writing A, I, J, K for a three-dimensional array, it's much easier to write first element's address and multiply by some I, J and K by some value and go to the linear address referenced by it. Otherwise, pointers are useful when you don't want consecutive elements. So linked list pointers are a must. How to remove loops and what are the fast and slow pointers used for? So again, this is irrelevant. There is nothing like a fast and slow pointer for us. Okay. For pointer in the language level is just a pointer, so don't worry. How to remove loops in linked list? Not clear to me. So what do you mean loops in linked list? Please differentiate between two pointer arithmetic operations. Which pointer arithmetic operations do you want to differentiate? That's not clear. Is pointer comparison operation? Okay, so there are two questions. Let me take a look at it. Pointer comparison and pointer subtraction only work for arrays. Is pointer comparison and pointer subtraction? Okay, so let me now give you some generic answers. You can keep asking, so I can keep answering. It will not end. So I should tell you a trick by virtue of which you can get the answers yourself. Satisfactory. So I'm looking at Alka Mohan or whatever question which says is pointer comparison operation and pointer subtraction only work for arrays. Okay. So what is pointer comparison? Pointer comparison is P less than equal to Q if P and Q are pointers. So this is what a comparison will mean, or it will say is P equal to Q. These questions are all comparison operations. Pointer subtraction operation is P minus Q if you want to subtract two pointers. Firstly, this is always on because you can take two pointers and compare. There is no issue out there. So how do you check these out? The best is to write a small program, small C program. Do that arithmetic and see. So you write a C program with whatever your doubt is. So I want to see, can I do P star Q where P and Q are pointers? Write a program. Submit it to the compiler. There are two possibilities. The compiler will say error. Then you know that the language does not permit it. It is not permitted. This arithmetic is not permitted by the grammar. Compiler passes it. Okay, then you know the language has no issues, but it can give you runtime errors because you do something silly. Okay, so what you are essentially asking is, does the compiler allow or not? Okay, so if you are looking at comparison is whether two pointers are same. You can ask it anytime. For example, I have a linked list. Sorry, I drew an array. Don't worry about what the linked list is. And I have created two pointers who are racing through this linked list. Two different people are chasing the linked list, which means two pointers. I can always ask, has P become equal to Q? Have they caught up or have they not caught up? Now in this sense, whether P is less than Q or greater than Q does not matter for the linked list. Because the heap, the elements are arbitrarily given. This address could be greater than this address or less than this address, depending on where it was found. The person who comes in last may get a ground floor room. The person who came first might have got a third floor room. Doesn't really matter. It's all that they have got a room. So coming back, pointer comparison is meaningful only with P equal to Q or P not equal to Q. This only makes sense in the pointer board. Are two pointers the same or they are not the same? Whether they are less or equal does not matter. It can matter only with arrays because they are consecutive. The next was subtraction. Pointer subtraction does not make sense. If this is 2000, this is 1000, what does the difference mean? So when you do pointer arithmetic, the pointer arithmetic typically says you can only do this, where C is a constant. So I had given you right in the first lecture, lot of programs where segmentation faults were created, right? So your question whether I can take anything and somebody has asked whether I can take only arrays or you can do any object and do an arithmetic, the answer is you can take any object. For example, if this is my area on the stack and I have a big structure out here and the starting address of the structure is P, I can add any constant to it, okay, and I can ask it to be dereferenced. It's my risk. If this goes outside the area, I'll be thrown out. So any pointer to any object, you can do a plus minus constant, and that will be allowed by the compiler. The compiler does not know what you are doing. Okay? There's no way to check whether you are inside the area or outside, so that is only known at runtime. So plus minus arithmetic with constants will go through, but if you dereference your segmentation fault, if it occurs, then the user or the writer of the program is responsible, not the compiler or the OS. So pointer subtraction works for any pointer. With arrays, it may be a little more definite, because arrays people use it to do meaningful things. If I want to go from a of ij to another element a of I plus 5 and j minus 2, the compiler will do a very elaborate calculation. I'm not giving you all that, it's a matter of compilers. But if somebody knows how much distant away these are, I can move the pointer back or forth and access this element. So if I know this address through a P, I can do some P plus minus C to reach another array location. You should know, of course, what this C should be. If you know that. So arrays, it makes a lot of sense because I can avoid a lengthy array calculation. It's very expensive to calculate these things, 8i plus 5 j minus 2. That's how compilers work. But if you can do a simple arithmetic and reach, you will make the program efficient. However, it will also be very unreadable. Okay, then will the entire linked list be stored on the heap? The answer is yes. All dynamic data structures fully are stored on the heap. It doesn't make sense to put on the stack because you don't know how big that will be. And a stack must have fixed memory. So the entire linked list, entire hash table, entire graph, all such things will be on the heap. But to enter the heap, you need the gate, you need the key. The starting address will be on the. Will malloc return a void pointer? Typically it will not, but you can force it to return. Typically malloc is supposed to return a pointer, and if you observe, after doing a malloc, right, we did a malloc like this, and then how you cast it is up to you, what type. So if you don't want it to point to anything, you can make it void star, but with the consequence problem that it may be. By default, malloc returns an address. Casting that address to a type is our business, and if you do this, then it will do a write. Okay, so this is done. Let me see if I have missed something out here. More questions are there. Let me reach the end of your question so I can see everything. How can you represent multivariable polynomial using a linked list? You can, but you can see now we are getting into a more complex issue. So once you ask these questions, first I will ask what sort of multivariable polynomial you want. If you want really multi, then we'll have to really think complicated. But suppose I have a polynomial in 3 variables, x, y, z. Right? So what do I need? I know that an arbitrary term will have one coefficient, let's say 5.0. It will have some power of x, say n. It will have some power of y, say m. It will have some power of z, say p. So if you fix the maximum number of terms in the multivariate, 2, 3, then I know the shape of each term, and therefore I can immediately decide what should be my structure. So one for the coefficient, one for the first variable, right, the power, exponent for the first variable, exponent for the second variable, and exponent for the third variable. This was fixed. Now suppose you say, no, I don't know. It can be up to a 10 variable multinomial. So I don't know, 10 variables. Then instead of doing this, what somebody can do is, okay, since you are not sure, it can go up to max 10. What I can do, I can create an array here up to 10, which are my exponent 0 to exponent 9. What if some term is only z, it doesn't have the other bit, I will put the exponent as 0. So those terms which are missing, the exponent will be 0. The other 10 variables, depending on who is present and what is the exponent, I can store it. So designing the data structure is not an issue. The issue will be how do you code the operations? What are the operations on a multivariate polynomial and how they can be done, whether it is differentiation, integration, whatever. So the point is storing only needs going a level down and seeing how does the term look like in maths, deciding how many values, and immediately decide one node of the data structure. And since it's a singly linked list, I don't have to worry, I can just chain them together in some order. However, if you wanted in this sorted in powers of x or y or z, then that will give you more interesting. Now what is rehashing? I've forgotten, I just do. How Q is different from stack? I think in this course, I can only give you a very quick answer is not a proper data structure course will do much better. So it's like this. A queue is a structure with, just like a human beings form a queue at the bus stop, right? So organize elements so that they are in some order. At one end people leave and at one end people join. This is the queue. Okay, and if you strictly follow a queue, unlike the real life scenario, nobody can join in the middle, howsoever important, and nobody can leave from the middle also. You're supposed to stay put. A strict queue will order this. So basically you observe that strict queue has two ends, and disciplined way only one person can leave, which is at the head of the queue, and only one person can join, or one or more can join, but only at the end. Contrast to this, the structure of a stack is one over the other. And stack, you only can look at the top element like a stack of plates. You're not supposed to know how many elements are on the stack. You're not supposed to ask who is at the bottom of the stack. None of these are allowed. So a stack has only one active end. Everything happens at this end. For example, if you have organized in a parking area, car parked by stack, then only the last fellow who has come in can leave. Everybody has to wait. Till the fellow leaves, nobody else can pull the car out. Right? So it's not a good organization for parking. So stacks and queues are very differently organized structure. Typically they are linked lists because we don't know how many elements will get into them, and they are used to solve different kind of problems. So let me give you one example. Somebody had asked me on the last time, if you use a queue, somebody asked graph. Queue is always used to traverse a graph in a breadth first search. If you know, figure it out, I can't explain here. If you want to do a breadth first search of an arbitrary graph, queue is an absolutely natural data structure for it. Whereas there is another traversal called depth first search. If you want to do that for a graph, then the natural data structure is a stack. So there are many such examples where the operation dictates a certain data structure, because that's the natural way of solving that problem. So stacks and queues are widely different applicability. Typically you don't use one when the other has to be used. Multivariate polynomial done. Can we apply binary search in linked lists? Okay, so here is a question. How do you like to answer? If you want to apply binary search, you can just you can treat it as a conceptual question. So there is a spirit of binary search. A binary search says that if I have a collection, right, this is typically done with arrays. I know the first element, where it is. I know the last element, okay, and these are sorted, which is very, very important. And it says if things are sorted, I can look at the middle and decide on which half the element I am looking for resides, on the left half or the right half, right? This is what it does. Since it is sorted, it cannot be in both halves. So by looking at the middle, I decide which direction I should organize my search. So it requires three things. I must be able to access the first element, I must be able to access the last element, and I must be able to access the middle element. So here it goes now. If I have a linked list allocation, and if you want to use binary search, you can ask for yourself how this will go through. Here is my list. I can, if you are very keen, definitely give you a pointer to the last element also. It is not too difficult to maintain. So a queue, for example, has first and last, so which is also a linked list. But it will be very difficult, even if I give you one pointer to the middle, which I can. As my list is getting built, my middle pointer is also changing. Okay? If you remove one element, my middle will move one to the left, one to the right, etc. I have these three. The trouble here is, even if I have this and I figure out, let's say I was looking for 25 and this middle element happens to be 35 and it is sorted in ascending order, increasing values, then I know 35 is in the first half. But I don't know in this list where is the middle. So just having one middle will not help. If you want to do a binary search, you will need a series of middle pointers. Okay? And that, if you can do it meaningfully and quickly, then binary search is fine. But if you have to figure out every time the middle element and waste time, then searching through the list will be easier. You don't have to do this. So binary search on a linked list will not directly easily work because you don't have access to the middle element or an arbitrary position in the list. What is the size of generic pointer in C? Pointers in C are always 8 bytes. only case of generic pointer, it doesn't say what it points to, but the storage that is allocated on the stack for a generic pointer, all pointers are on the stack, generic pointers, is 8 bytes according to me for a new system or an architecture which has come in the last 2 to 3 years. What happens when we don't free the node we delete? Okay, it's like if you don't free, for example, if you go to a restaurant, okay, you eat and you don't clean up your table, right? If you clean up, it's good for you, you can buy more things and eat again. If you don't, then once you leave, the system will clean it up, right? So similarly, when your program quits, the heap area is restored back, but while you are working, nobody is going to clean up. So it may happen that you need more nodes, and since you have not freed, your heap is exhausted. So freeing a node is basically clearing more place for oneself. If you don't free the node, there is no damage to the system, to the operating system or the compiler, but as soon as your program is over, everything is reclaimed back. It becomes a property of the system. But while you are running, you can do yourself, or I can do myself a favor by freeing the nodes which I don't need, so that when my list grow heavily, I've also freed things and made the list grow more. What is the representation of a linked list in memory? It's basically a pair of boxes. As I told you, these boxes are my linked list, value and address. If you have a doubly linked list, value and 2 addresses, and so on. So a linked list basically is a packet which is linked through memory inside the heap, which is also a part. How to remove loops in linked list is not very clear. If you have a circular linked list, then you have purposely created a loop. Okay, you want to keep going back in circles, in which case you don't want to remove this loop, you want to continue. Otherwise, your looping in such linked list should not happen, because when you traverse a linked list, it goes from a start address to the last node and then it will stop. It might at best give you a segmentation fault, but there is no looping. Looping in linked list is only possible if you have a list like this, for which you will have to be careful. If you use a circular queue or any such thing, something like this, and this is your list, then your list has a natural cycle, and if you don't stop it properly, for example, finding the length of a list. If you don't know where to stop, this fellow will find out there are 10 elements, come back and 10 elements and keep going in cycles forever. Okay? So looping in a linked list may arise because you have a circular linked list, but then people know how to do that. They will say whenever P is not equal to next of P or something, whatever, you can figure it out. Okay, so this pointer that you have, the list pointer, is not been traversed already. You can know where to stop. So you can put a condition which checks circular. What happens? I answer that. What is the representation of linked list in memory? So if we're talking about stack, then it's just a pointer. If we're talking about a heap, it's disjoint locations linked by U. Slow and fast, as I said. What is the use of pointers? Double hashing I did not. Okay, there are some other questions. So what is hashing I have not explained. So maybe I will just in a minute, let's see how much time do I have. I have 1 or 2 minutes. So what is hashing firstly? So hashing is a function which takes a key and then produces a value. What it is used for? It is this value is used to store the value in a table, as I told you. So for example, if I give you my name, which is this, and somebody says my hashing function will be to take the number of letters in a name. And how many does mine have? It has 9. So this will produce the value 9. So in the 9th location, I will go and store my name, and any string which has 9 letters will also be stored here. So this could be a hash string. So this function is the hash function. So why do you do double hashing or more hashing? So it's quite possible after hashing, I find that there are many names with 9 letters, okay, which may or may not be true in general, and therefore one element of this list has become too long. Not all lists are of equal size. I would like them to be of equal size so that I can go to one place and search that list. So if this becomes too long, which means my hashing function is biased, it's not doing the right thing. It's taking any number and putting it in the same location. So then people say, if this is so, please don't do this, don't immediately install. So apply yet another hashing function, okay, maybe on the key or whatever, and then finally use it. So this is double hashing. So if single hashing gives you a lot of conflicts, if this causes a lot of conflicts means too many elements of the same value is the nature of the hashing function. Then what you do quadratic hashing or double hashing, you hash again, hoping that the new value produced will distinguish between two 9 characters. I can do that. For example, I can say, if two names have the same number of letters, find out how many vowels they have. That's my second hashing. So under the second hashing, F1 will give me 9, but F2 of the same value could give me, mine has 3, so 3. And therefore it can get distinct. So double hashing says if you cannot get away with one function, then use more functions to distinguish between entities which are looking similar. Alternate ways of overcoming the dangling. So dangling pointer typically will not come if you are doing things properly. So it's usually the lack of discipline which causes dangling pointers. So coming back to this, where do dangling pointers come? The dangling pointers come when you create from using malloc a pointer on the heap. Free this point, typically is a pointer p on the heap, you free it and then try to use p because you forgot it. So this is not correct. Once you have removed it, then this is not done properly. So dangling pointer means if you create a pointer, please initialize it. Please check before dereferencing a pointer whether p is 0 or not. Check the pointer value, whether p is legal or not. Okay, and then this will not happen. So these are the big point problem when in the days of Pascal long back. Right now it's not a major issue if you do good discipline program. Segmentation fault, I have told it many times and giving you examples also, maybe for the last time. If you generate an address which is outside your range, then segmentation fault arises. So if your working program wants to address location 10,000, how has it gone to 10,000 you should ask yourself, and 10,000 is not in your area, then it's a fault. It's a segmentation fault because memories are divided into segments by some old terminology, and it has gone outside the segment to which your program decides. Can we deallocate heap memory without starting address? It is not clear to me. So you deallocate heap memory by using free, and the syntax for free says you must give it a pointer. Okay. But remember, this only deallocates one address. Suppose, typically again, if you have a big data structure, you have a big linked list, and you have found my job is over, I want to remove this entire linked list. You want to free the entire list. Then freeing this list will not do. It will only remove this pointer. All of this will remain on the heap occupied. So then I have to write a routine which calls free so many times. I first free this element, take the address, free the next element, and I have to do it yourself. So I have to write a function so that I remove the complete data structure. It is not done automatically. Okay, the job is ours. Free only frees one pointer at that address, and depending on what it is pointing to, it will free the whole thing. If P is declared to be of size 20, then 20 bytes are free, but it will not free the entire collection. So you can deallocate memory. You have to deallocate one pointer at a time, and if you don't need the whole data structure, please remove the whole data structure. So there are no uses of dangling pointer. It's basically an error in the program. You should not have a dangling pointer if you have written the program correctly. They are the causes of most runtime errors. What is a multi-list? So a multi-list, typically I'll treat it as a multi-linked list. This is the last question which I'll take. So multi-linked list says that you will have more than one linked fields. For example, take a binary tree. Every node has a right child and a left child. So it has two links. So it's a multi-linked list. I've given you a picture of a sparse matrix which has 4 linked fields. So it's a 4 linked field and so on. So depending on the application, you decide how many elements it should be linked to, and that decides how much multi-linking the data structure requires. Typically 3 or 4 I have seen are mostly enough for most applications. Okay, so I think time is up. So wish you error-free programming, happy programming with C. Thank you.